concentrated sulfuric acid at 180 degrees Celsius, hydrofluoric acid mixtures that dissolve glass, chloride process streams that pit stainless steel within weeks. The silicon carbide shell and tube heat exchanger handles all of them in one tube bundle, through walls just a few millimeters thick, transferring heat at 120 watts per meter per Kelvin. For engineering metrics, anchor heat exchanger duty. Thermal conductivity reaches approximately 120 watts per meter per Kelvin, roughly twice that of corrosion-grade stainless steel. Flexural strength exceeds 350 megapascals. Compressive strength exceeds 2,200 megapascals, enough to support proof testing up to 186 bar. And hardness sits at Mohs 9.5, second only to diamond among industrial materials. The tube body is pressureless direct-sintered alpha silicon carbide. Distinct from reaction-bonded silicon carbide, which contains 8 to 12% free silicon, direct-sintered alpha silicon carbide has none. The full-density matrix is chemically inert across the complete pH range, surviving concentrated mineral acids, halogen acids, oxidizing chemistries, and caustic alkali solutions. Thermal expansion stays near 4.5 micrometries per meter per Kelvin, low enough to prevent thermal shock cracking under rapid temperature swings. Standard outer diameters cover 14 mm and 19 mm. The dominant dimensions in industrial shell and tube heat exchanger design, used by every major SiC heat exchanger OEM worldwide. Standard length reaches up to 4,000 mm, with dimensional tolerance held to plus or minus 0.3 mm for clean tube sheet fit and reliable seal performance. Custom diameters, wall thicknesses, and lengths are machined from drawing for non-standard heat exchanger geometries. Inside a silicon carbide shell and tube heat exchanger, the silicon carbide tube bundle sits in a steel or polytetrafluoroethylene shell. One fluid runs through the tubes, another runs across the tube bank inside the shell. Heat transfers through the tube wall by conduction. The two fluids never meet. Three things determine whether the heat exchanger meets duty over its service life. First, corrosion resistance. Sintered silicon carbide is essentially inert across the full pH range, surviving the concentrated acids and oxidizers that destroy stainless steel, hastolite, and graphite. Second, heat transfer efficiency. Silicon carbide conductivity at 120 watts per meter per Kelvin delivers 18 to 22% higher heat transfer coefficient than equivalent glass tube exchangers, smaller shell, fewer tubes, lower capital cost. And third, pressure and abrasion endurance. Flexural strength above 350 megapascals plus Mohs 9.5 hardness keep the tubes intact under recirculating acid loops, slurry-laden streams, and the cleaning cycles that wreck softer tube materials. Together, these properties make silicon carbide shell and tube heat exchangers the working answer for chemical processing, acid concentration, pickling, fine chemical synthesis, and pharmaceutical manufacturing, the duty where graphite and metal have reached their limit.